on? Okay. So I've got a string here, and this isn't just an ordinary string. This is an elastic string. That means it's stretchy. Okay? So what I'm able to do here is I'm able to use this thing and that thing to create waves in a string, and I'll explain just how that is, but I want to focus on this thing first. Turn that over. Okay, so right here, on this end, do y'all see this pulley? I've got the string tied at the opposite end, and here it's being allowed to dangle with this weight. Okay? It's an elastic string, so when I put the weight on it stretches out. So if I wanted to stretch it more, I could put more weight on there. If I wanted to stretch less, I'd put less weight on there. What's the point of me being able to stretch this? Okay. So what is the tension? If I change the tension of the string, what does that change? The speed of the wave. We're changing the medium, so we're changing the speed of the wave. So if I put more weight on this thing, what would the speed of the wave do? It would increase, right? Likewise, if I put less on there, it would do what? It would decrease. Turn that back over here. Okay. So this thing is called a string vibrator. Ah, look, it's a string vibrator. So what's going to happen here is I'll use this. This is a sine wave generator. It'll make sine waves, and it will cause this thing to move up and down and put waves into the string. And so you can think of this like just a piece of string. You can think of it like the surface of the ocean. You know, if I push here, a wave will propagate out. You can also think of it like strings on a guitar or piano or a violin, anything like that. So I'll go ahead and turn this thing on, and I'll turn my frequency all the way down to 1. So if you look carefully, you can see that this thing is moving up and down. It has a frequency of 1 hertz. What does that mean? You're getting 1 wave per second. Everybody agree? Okay. So now this isn't terribly interesting, even with the amplitude turned all the way up. What we want to see here is what's called a standing wave, like I created with the wavetable a few moments ago, and like you created with the Slinkies last class. So to get a standing wave, this standing wave depends on this distance here. I can't just create any wave I want. It depends on this specific distance. So in order to create a standing wave, I can play around with it. Luckily, I've already done some research. Now this is what's called the fundamental, right? The entire string, and you could have done this with your Slinky, is moving as one big piece. Do y'all see that? It's going down and up, and down and up. Okay? Is this a whole wave?
No. Well, it doesn't have a trough and a crest at the same time.
It doesn't have a trough and a crest at the same time. So this is not a whole wave. This is what? Half of a wave. So the entire wavelength would be from here to here, doubled. Okay? So, the frequency here is about 4.4 hertz. That's the fundamental. And any fundamental, wherever it's being created, whether it's being created in, like inside of an instrument, like a tuba or whatever, this is the lowest frequency possible. Okay? So for this particular string, this is the lowest frequency possible. If I was to stretch this out and give it a different speed, I could get a different fundamental frequency. Alright? So it's important that you know that. So what I'm going to do now is I'm going to double my frequency. I'm going to go from 4.4 to about 8.9. So my question to you is, will that change the speed?
No.
No. The speed will stay the same. However, y'all remember the wave equation? What's the wave equation? It equals
1
something y, upside down y.
F wavelength. Frequency
F
times a wavelength.
Alright? So if this stays constant and I double this has to do what?
It has to half.
It has to get half. So let's do that. There we are. So, do y'all see that I have a full wavelength here?
Hey, there it is.
So here, I've got a crest or a trough, and here I've got a crest or a trough. What do I call that? I can't call it a crest.
A blur.
I can't call it a blur, a big blur. Right? To be more scientific, we call these sections, we call them antinodes. Right? And an antinode is an area of maximum displacement. Okay? Now the opposite of an antinode is just a node. And notice that this area is a node. Right? There's also nodes on both ends. Okay? The node is a point of, node means no vibration. Y'all got that? No vibration, node. So an antinode, anti means not node, so it's not no vibration. That's English for it.
Not no.
Alright? So node, no vibration, not node, vibration. So this is maximum vibration. Now a lot of students they see this and they're like, oh, it's two strings you've got going there. I only have one string. And I can prove that because I cannot put my finger in between. There's no in between, it's just one string moving at a rather high frequency. So what I'm going to do here is I'm going to double again. So about 15. So here I've doubled it, so now I've got two wavelengths here. So how many antinodes? Count them with me. 1, 2,
3, 4.
4 antinodes. How many nodes are there? 1. Now in this particular setup, you always get one more antinode than node. Alright? So now what I'm going to do here is we're going to turn off the lights. And if I use a strobe light, you can actually see that it's just one string.
That is trippy.
That's so weird.
Yeah.
Crazy.
Get it at the right frequency. It won't look so weird.
That's cool.
Well, even that not at the right frequency, you can still see that it's just one piece of string moving up and down. And you can see that most of the time it doesn't look very uniform. See how it's got like bulges and dips? That's because it's not just one wave, it's a standing wave. It's a bunch of waves put together. So let me go back to... So this is just my one wave. Do y'all see that? Let me slow the strobe down. There we go. So now it just looks like it's moving really slow.
Oh yeah, that's cool. That's
Alright.
cool.
So here it's moving at 9 times per second. So this thing is moving up and down almost 18 times per second. You know, once for crest, once for trough.
But that's at the 8.9 hertz, right?
Yeah, this is at 8.9 because I've got one wave
like
here.
it. That's so
Okay? So if I wanted to calculate the speed that this wave is traveling at, this wave is traveling at, I know my frequency. How would I get my wavelength?
so cool, right? You need to make YouTube videos of this.
How would I get my wavelength? If I'm looking for my speed, I can't use that equation.
Use it from half to half.
I can measure it. I can get out a meter stick and measure the sucker. Does that make sense?
Yeah.
It's a wavelength. I can measure the length. Alright? Stop that.